Sir, your voice is not coming.
Am I audible now?
Yes, sir.
ఇప్పటిదాకా వినబడలేదారా నేను? Is it okay now?
Yes, sir.
Yes, sir.
ఓకే రా. ఇంతదాకా వినబడలేదా మరి?
No, sir.
స్టార్ట్ చేసినప్పటి నుంచి? అవునా?
No, sir.
ఓ 1 సెకండ్. అంటే దీంట్లో లైక్ ఐ హ్యావ్ 2 or 3 థింగ్స్ లైక్ మోనో స్టీరియో అని 2 వస్తున్నాయి. సో ఓకే ఓకే. ఇప్పుడైతే బాగానే వినబడుతోందా? ఇంకా జనాలు ఎంటర్ అయ్యే వాళ్ళు ఉన్నట్టున్నారు. ఓకే. Now, see when carbene is added, it gets connected to the double bond. I mean an alkene across the multiple bond. This is how it gets connected. Look at this. This is the CH2. Okay. Let me give you an example. See if we consider this. This, of course, is a cis compound. When a singlet carbene is connected, remember, when a singlet carbene is connected, in this case it is this product what we get. If you have started with a cis 1, you will end up with a cis 1. Okay. See, in general, we consider as singlet carbene with singlet, it is a stereo specific. I mean, if you take a cis 1, you will end up with a cis 1 only. So in this case, it is stereo specific. Whereas with the triplet, there is no special stereochemistry. So this is very important. If you start with a cis 1, you will end up with a cis 1 with a singlet carbene. Remember. Okay. Now let us consider one more interesting example. Now suppose if dichlorocarbene is added. Dichlorocarbene is in fact produced from chloroform. So this is chloroform. Now to this chloroform, when alkali is added, this is what happens. Let me call this alpha alpha or 1 1 elimination. We have seen this. The basic classification gives us alpha, beta, and gamma eliminations. Now, as and when the OH minus subtracts the H plus, we get this called dichlorocarbene. This is dichlorocarbene. Along with that, you get water, then Cl minus. Even this dichlorocarbene, remember it's an electrophile. Because the central carbon, I mean this carbon has got only 6 electrons in its valence shell. I told you that it is called sextet, just like octet. Okay, so this is an electrophile because it has a sextet of electrons. Very important. It appears as if it is a nucleophile with this pair of electron. No, it is not a nucleophile, it is an electrophile. Generally, when we see a pair of electron at something, at a particular atom, we consider it to be a nucleophile, or we feel as if it is ready to donate a pair of electron. No, this is something which accepts a pair of electron. Has to, because to get octet, it needs to accept a pair of electron. So that is an electrophile. Now let us add this dichlorocarbene to an alkene. Yes. So this is cyclohexene. Now when dichlorocarbene is added to this, okay, what happens? As per the mechanism, add this across, just a second, goes to carbon. So anyway, the dichlorocarbene is added across the multiple bond. Okay, carbon with 2 chlorines. Now it undergoes some modifications. Let's see. As and when it comes here, this goes off. Right now, come on. Up to this it is okay, then take it this way, and even this bond has come here, so this becomes a double bond. I mean, this bond has come here. Okay, then the carbon which has still got a chlorine, Cl minus is anyway last, and now this carbon is still holding the bond with carbon. Come on, let us show it this way. Oh no, once it is this. Okay, now it is clear. But see, because see earlier this bond was between these two carbons. This carbon is still holding the bond here, whereas this one has lost. So let me put a positive charge here. This one. Okay. Because this carbon has lost its bond, this one is still retaining the bond. Now this can be written as, come on, it is now with 7 carbon atoms. Okay, this. Now with 7 carbon atoms, you can write it this way, right? Where is a positive charge? It is at the carbon adjacent to the carbon which has got a chlorine. Yes, this one. Okay. Now take a hydrogen out so that it can come to the rescue of the positive charge. Take it this way. Right. Now you get something of this type. A double bond here, then a double bond. Yes, they are in conjugation. That is, of course, a more stable system. Okay. When if suppose 2 pi bonds are in conjugation, you'll have more resonance stabilization, right? Check this out. This is how a carbene is added to an unsaturated system. Now, just like carbenes, we have some other species called carbenides. In fact, in fact, carbenides are better, advantageous when compared to carbenes. We'll discuss about that later, but for now, let us see the basic reaction. First of all, what is a carbenoid? A carbenoid is something where the carbene is bonded to a metal. Okay. When a carbene is bonded to a metal, we call it carbenoid. Let us take the same reaction of ethylene with a carbenoid. Let me show you what a carbenoid is. Now, this is carbenoid. Then how is this carbenoid formed? See, it can be formed by treating methylene iodide. Methylene iodide on reaction with a zinc copper couple gives iodomethyl zinc iodide. See, this is iodomethyl zinc iodide. Okay. Let me write that. Iodomethyl zinc iodide is, of course, a carbenoid, wherein a carbene is bonded to a metal. Now, look at this. See, basically, this reaction of the formation of iodomethyl zinc iodide from methylene iodide and zinc copper couple is called Simmons-Smith reaction. Okay. Of course, the overall reaction is the same. addition of CH2. That's it. You got a CH2. Okay. Along with this, of course, you get ZnI2. Right? So this is how the carbenides are added. Let me give you an example. See, when cyclohexene is treated with, say, iodomethyl zinc iodide, we get this. Just add a CH2 across the multiple bond. Simple. Okay. Now, what are the advantages of carbenides? Let me tell you. You know, carbenes are very expensive. At the same time, they are more reactive. See, because they are more reactive, they not only add up across the double bond, they also insert into carbon hydrogen bonds. Not only the carbon double bond carbon bonds, but they also insert into carbon hydrogen bonds. They are more reactive, so they insert into carbon hydrogen bonds also along with the C double bond C bonds. So this is the problem with carbenes. See, the reaction of carbenes with double bonds is what is intended, but even they insert into these bonds. So that is the problem with carbenes. Because of the insertion of the carbenes into CH bonds, you know, whole lot of byproducts are also formed. Due to this, several byproducts are formed. So this is a problem. Okay. To avoid this, I mean, only to add up across the multiple bond, we go for carbenoids. Okay. So this is about the addition of carbenoids. Okay. Next. Now let us go for the insertion of nitrene or say addition of nitrine. You know, nitrines are also a type of reactive intermediates, just like the carbenes. If we consider ethylene, take RN3. Alkyl azide, R plus N3 minus, kind of. In the presence of sunlight or heating, you know, you can actually go for this. Okay, this is what you get. Yes, of course, this is what is been inserted or is added across the multiple bond. Now, along with this, we also get a byproduct. Look at the byproduct. This is a byproduct. Now, let us see the mechanism. I mean, what is alkyl azide? See, this can, of course, be shown as R, N, a lone pair, double bond, N, then this. Look at how it is written. This gets a negative charge, and this gets a positive charge because it has only 4 electrons. So gets a positive charge as it has 1 electron less than what it has to have, whereas this one has got negative charge because it has 1 electron more than what it has to have. So this is how nitrine is inserted across the double bond. Okay. Next, it's a reagent called Lemieux reagent. See, it's of course Lemieux. There are 2 types of reagents. One is Lemieux-Redloff reagent, and the other one is Lemieux-Johnson reagent. One second. See, Lemieux-Johnson reagent is sodium. Just a second. Let me give you Lemieux-Johnson's reagent first. It is actually a mixture of osmium tetroxide with sodium periodate. So this is osmium tetroxide, and this one is sodium periodate. Okay. Now, let me first tell you what happens with this particular reagent. How does it get added? Taking this, if osmium tetroxide sodium periodate is used, one second. Then this will give us a product with two hydroxyl groups. Okay. Only if osmium tetroxide is used. But with, just a second. But with this, we have already seen it's a syn hydroxylation reagent, the first step. Now, in the second step, if iodic acid is considered with osmium tetroxide, it becomes periodic acid. Periodic acid. Okay. When this periodic acid is used, let me show you what happens. Let us consider this. RCR, something which is unsymmetric. With periodic acid, I mean overall, you get R C double bond O R from this area. From the other end, you get R dash C double bond O H. Okay. See, initially, if you consider only osmium tetroxide, this is the overall reaction, of course. That means with osmium tetroxide and sodium periodate. But what happens at the beginning is only with osmium tetroxide, you get a syn hydroxylation thing, as I said. It involves two steps. Across the multiple bond, add the two hydroxyl groups. This is what you get in the beginning. But then with the periodate ion, IO4 minus, this IO4 minus gives the final product. I think I need not write. It's already there. So let me show you this way. Yes, this is what we get. So with Lemieux reagent, I mean Lemieux Johnson reagent, we get a syn hydroxylation product because of this osmium tetroxide, and then because of the periodate, the bond undergoes cleavage to form a ketone and an aldehyde. Okay, that's it.